Swayam Prabha. Digital India. Educated India.
Dear all, in continuation of random variable, we have to discuss some more problem and once again recollect that random variable so that you can understand the problem. So, the definition of random variable says that it is a function from a sample space of an experiment to the set of real numbers. That is, a random variable assigns a real number to each possible outcome. For example, suppose that a coin is flipped 3 times. Let x of t be the random variable that equals the number of heads that appear when t is the outcome. Then x of t takes on the following values, that is x of 3 heads mean 3 and x of 2 head and 1 tail is x of HTH, HHT and x of THS. Therefore, total number of head is 2. So, this is the way we can write the random variable, and then x of TTH, x of THT and x of HTT. So, we can write the random variable as 1 and x of 3t is 0. So, this way we coin the example 1 of a random variable. Now, keep it in mind this example. Further we can discuss the definition as well as related problem. Now, we have a definition. The distribution of a random variable x on a sample space S is a set of pairs r comma p of x comma r for all r in x of s, where p of x equal to r is the probability that x takes the value of r. Those set of pairs in the distribution is determined by the probability of x equal to r for r belongs to x of s. Example 2, that each of the 8 possibility of outcomes where a fair coin is flipped 3 times has a probability 1 by 8. So, the distribution of the random variable x of t in the previous example 1 is determined by the probability of x equal to 3 is equal to 1 by 8 and the probability of x equal to 2 mean 2 head occurred is 3 by 8, 1 head occurred is 3 by 8 and the probability of x equal to 0 is equal to 1 by 8. Consequently, the distribution of x of t in example 1 is the set of pairs according to the distribution 3 comma 1 by 8 and 2 possibilities of head corresponding is 3 by 8 and 1 possibility of head corresponding 3 by 8 and 0 possibilities of head corresponding 1 by 8 is the probability. So, this way we can write random variables of getting the possibilities of head 3 times like that. So, keep it in mind this example and we will discuss one problem with name of example 3. Let x be the sum of the numbers that appear when a pair of dice is rolled. What are the values of this random variable for the 36 possible outcomes I comma j, where I and j are the numbers that appear the first die and the second die respectively when these two dice are rolled. So, the random variable x takes on the following values, right. If we have possibilities of what 2 dice is throwing and corresponding random variable we have to define. First die appear and second die appear, and then these are all the possibilities of a random variable we can write, and first one is for I and second one is for j. So, that I plus j equal to 2. So, that x of 1 comma 1 equal to 2, x of 1 comma 2 equal to x of 2 comma 1 is a possibilities. So, I plus j is 3, x of 1 comma 3, x of 2 comma 2, x of 3 comma 1. So, I plus j equal to 4, x of 1 comma 4, x of 2 comma 3 and 3 comma 2, 4 comma 1. So, that I plus j equal to 5. If I plus j equal to 6, then the possibilities are x of 1 comma 5, 2 comma 4, 3 comma 3, 4 comma 2 and 5 comma 1. If I plus j equal to 7, then x of 1 comma 6, 2 comma 5, 3 plus 4, 4 plus 3, 5 plus 2 and 6 plus 1. If I plus j equal to 8, then 2 comma 6 1 possibilities, 3 5, 4 4, 5 3 and 6 2. Similarly, if I plus j equal to 9, then it becomes 3 plus 6, 4 plus 5, 5 plus 4 and 6 plus 3, then corresponding I plus j is 9. And for I plus j equal to 10, we have 4 comma 6, 5 comma 5 and 6 comma 4. If I plus j equal to 11, the possibility is 5 comma 6 and 6 comma 5. If I plus j equal to 12, then it has 6 comma 6. So, these are all the random variable of possible outcomes. So, this way we can denote random variable. Next, we are going to discuss the interesting problem is birthday problem. A famous puzzle asks for the smallest number of people needed in a room, so that it is more likely that not that at least 2 of them have the same day of the year as their birthday. Most people find the answer, which we determine in the following example to be surprisingly small. After we solve the famous problem, we will show how similar reasoning can be adapted to solve a question about Ising functions. So, the example is the birthday problem. The statement is, what is the minimum number of people who needed to be in a room so that the probability that at least 2 of them have the same birthday is greater than of. So, this is a question. Now, we are going to discuss the solution to the problem. First, to find the probability that at least 2 of n people in a room have the same birthday, and calculate the probability Pn that these people all have the different birthdays, then the probability that at least 2 people have the same birthday is 1 minus Pn. For computing Pn, we consider the birthday of n people in the same fixed order. Imagine them entering the room one at a time, we will compute the probability that each successive person entering the room has a birthday different from those people already in the room. Now, the birthday of the first person certainly does not match the birthday of someone already in the room. The probability that the birthday of the second person is different from that of the first person is 365 out of 366, because the second person has a different birthday when he or she was born on one of the 365 days of the year other than the day first person was born. So, this assumption is equally likely for someone to be born on any of the 366 days of the year into this and subsequent steps. So, that is the meaning of the birthday of initially how we have taken corresponding to probability. Now, keep it in mind this, that the third person has a birthday different from both the birthdays of the first and second people, given that these two people have different birthday is 364 by 366. In general, the probability of jth person with j lies between 2 to 366 has a birthday different from the birthdays of j minus 1 people already in the room. Given these j minus 1 people have different birthday is, the favorable case is 366 minus of j minus 1 divided by 366, that is it becomes 366 plus 1 is 367 minus j by 366. So, this is the way we can choose for the people having the different birthday. Now, we have assumed that the birthday of the people in the room are independent. So, we conclude that the probability that n people in the room have different birthday is Pn is equal to 365 by 366 and 364 by 366 and 363 by 360 and so on, 367 minus n by 366. So, it follows that the probability that among n people that are at least 2 people with the same birthday is 1 minus Pn, which is equal to 1 minus of this value, that is 1 minus of 365 by 366 into 364 by 366 and 363 by 366 and so on, 367 minus n by 366. So, we have to determine the minimum number of people in the room, so that the probability that at least 2 of them have the same birthday is greater than of. So, we use the formula, we have found 1 minus Pn to compute it for increasing values of n until it becomes greater than of. So, there are more sophisticated approaches using calculus that can be eliminated this computation, but we will not use them here. After considerable computation, we find that n is equal to 22, therefore, 1 minus Pn is approximately 0.475, while for n equal to 23, 1 minus Pn approximately 0.506. Consequently, the minimum number of people needed so that the probability that at least 2 people have the same birthday is greater than of is 23. So, up to this I hope all of you can understand the probability and random process. So, these are all the possibilities we can understand how to write probability of a number or coin a toss, tossing a coin or shuffling a card, and then the various activities of the problem we come across, and how to write the random variable, random experiment. These are all the things we learned. Now, we are going to next model 9, that is digital systems and binary numbers. It is most important for data science and particularly cryptograph, steganograph and so on. Now, we have to learn the fundamental ideas about that digital system and binary numbers. So, the digital system consists of digital age and information age, digital computers, digital system, discrete information processing systems. So, I hope all of you know about the digital age and information age. No need to explain detail, but we will detailedly explain in the subdivision of digital age and information age. And next, digital computer is a subset of general purposes, and it has many scientific, industrial and commercial applications. A digital system consists of telephone, switching exchanges, and it has a digital camera, and it has electronic calculators and PDAs, and it also having digital TV. Discrete information processing manipulate discrete elements of information. Now, we have to discuss about the signal. The signal having the following ideas: an information variable represented by physical quantity. For digital systems, the variable takes on discrete values, that is 2 level or binary values are the most prevalent values. For binary values are represented abstractly by digit 0 and 1, and the words represent as F and T respectively false and true, and also the words represent L and H respectively low and high, and the words on and off, these are all the representation of binary values. And binary value are represented by the value of the ranges of values of physical quantities. Now, we have a digital system. A digital system is an interconnection of digital modules. To understand the operation of each digital module, it is necessary to have a basic knowledge of digital circuits and their logical function. Second point, a major trend in digital design methodology is the use of a HDL to describe and simulate the functionality of a digital circuit. It is important that students become familiar with an HDL based design methodology. Now, we are going to discuss decimal number. Suppose we have a number like that A5, A4, A3, A2, A1 dot A suffix minus 1, A suffix minus 2, A suffix minus 3 and so on. So, the in between dot represents the decimal point, and then the number AJ means A is a base or radix, suffix j represents the power, so that we can write in terms of the polynomial expression like so. This is the first digit, second digit, third digit, fourth digit, fifth digit. Therefore, 10 power 5 into A5, Next one is 10 power 4 into A4 plus 10 power 3 into A3, 10 square into A2 and 10 power 1 into A1 plus after decimal, that is 10 power 0 into A0 plus 10 power minus 1 into A suffix minus 1, 10 power minus 2 into A power minus 2, 10 power minus 3 into A power minus 3 plus and so on. So, this way we can write in terms of the polynomial expression of given number, that is integral part and decimal part. Further, we can give an example related to the above one. 7329 you take it. So, it has 7000, therefore, 7 into 10 cube, that is in the thousandth place we have a 7 and 100th place we have a 3, therefore, 3 into 10 square. 10th place is 2 into 10 power 1 and unit place 9 into 10 power 0. So, this way we can represent in terms of the decimal number. In general, form of the base R system is A suffix n into R power n plus A suffix n minus 1 into R power n minus 1 and so on, A suffix 2 into R square, A suffix 1 into R power 1 plus A naught, and then after decimal A suffix minus 1 into R power minus 1 plus A suffix minus 2 into R power minus 2 and so on plus A suffix minus m into R power minus m. The coefficient of Aj equal to 0 to R minus 1. So, this way we can write what general form of the base R system. So, this whole ideas comes under the binary numbers. Now, we have to discuss example based on the base 2 number. For example, 11010.11, the base 2 is 26.75 base 10. How to write in terms of the polynomial expression, that is 1 into 2 power 4 plus 1 into 2 cube plus 0 into 2 square, 1 into 2 power 1 plus 0 into 2 power 0, 1 into 2 power minus 1, 1 into 2 power minus 2, simply multiply them and add them, we have what this result comes. So, this is the way we can write the digital numbers, the binary base to the digital system of base 2. Similarly, for base 5, 4021, that is 4021.2, the base 5 is 4 into 5 cube, 0 into 5 square, because it is 100th place and it is 10th place 2 into 5 power 1 plus 1 into 5 power 0, and then after decimal 2 into 5 power minus 1, and then multiply and add them, we have what 511 base 10, 511.5 base 10. So, this way we can represent this number to the base of 5 number. Similarly, for base 8, what you have to do, 127.4 base 8 can be written as 1 into 8 cube plus 2 into 8 square plus 1 into 8 plus 7 into 8 power 0 plus 4 into 8 power minus 1, and we have 87.5 under base 10. And for base 16, we have B65F16. So, this represent 11 into 16 power 3, that is B, A, B, C, D represent corresponding to the numbers. B is 11, and f is 15. So, that b 11 into 16 power 3 and 6 into 16 square, 5 into 16 power 1, 15 into 16 power 0. So, that the resultant is 46,687 the base 10. So, this way we can represent what in terms of the base 2, 5, 8, 16 respectively. Now, so the binary numbers we have written in terms of 2, 5, 8, 16 base, and then we can have a base 2 of the numbers 11, 0, 1, 11, 0, 1, 0, 1 base 2 is 32 plus 16 plus 4 plus 5 equal to 53 base 10. For special powers of 2 is 2 power n, 2 power 10 is 1024 is kilo denoted by k, and 2 power 20 corresponding value is 1048576 is a mega and denoted by m. 2 power 30 corresponding value is 1073741 is giga denoted by g. Therefore, the powers of 2 in the table shows that n you take the value 0 and 2 power 1, 2 power 0 is 1, and when n equal to 1 it becomes 2, when n equal to 2, 2 power 2 is 4, n equal to 3, 2 power 3 is 8, similarly 4, 16, 5, 32, 6, 64, 7, 128 and so on. We can extend it to what 23 corresponding 2 power 23 is 8388608. So, like that we can write the powers of 2 in terms of the table. So, keep it in mind this, so that we can do for arithmetic operation. So, arithmetic operation with the numbers is in base or follow the same rule as decimal numbers. So, the arithmetic binary is based on single bit addition with carry, multiple bit addition, single bit subtraction with borrow, multiple bit subtraction and multiplication and BCD code of addition. For binary arithmetic addition, adjunct is 101101, addend is 10111, therefore, sum is 1010100. So, because 1 plus 1 is 0 and then carry on like that, it will come like that, right. For subtraction, we have minuend is 101101 and subtrahend minus 10111. If you subtract it, so that the resultant will be like this. For multiplication, multiplicand is 1011 and multiplier is 101, simply multiply. So, that first 1 and then 0, 0 of this, 1 of this, like this. So, simply multiplication method apply it and add them, you can get it. So, now we have a number based conversions for the name, radix and digits. For binary, we have 0, 1. For octal, radix is 8 and corresponding digit is 0, 1, 2, 3, 4, 5, 6 and decimal is 10. Therefore, corresponding 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and hexadecimal is like that 0 to 9 and then rest of them from 10 you call it as A, 11 B, this is 12, 13, 14, 15. So, this way we can represent hexadecimal, that is already we discussed the base 16, that is why the number convert corresponding to this. So, the 6 letters in addition to the 10 integers is hexadecimal represent this respectively. Number base conversion, for example, convert decimal 41 to binary and the process continue until the integer quotient becomes 0. For example, you take 41 by 2 and then we have 20 times divide, remainder 1, therefore, that 20 plus half, and take the 20 divide by 2, it becomes 10, there is no remainder 0, and 41 by 2 we have 20, right, and then plus 0 like that. So, this what we have to do, corresponding coefficient 1, y2 mean 1, 0, 0 like that. So, 41 by 2 corresponding 20 and half we have 1. Similarly, go ahead like that, we have what 1 0 0 1 0 1. So, this way we can represent the binary process. So, therefore, 41 base 10 can be expressed as A4, A5, A4, A3, A2, A1, A0. So, corresponding the representation is 1 0 1 0 0 1. So, this way we can convert normal number to the binary. So, we can understand from the previous base number base, then we have a conversion using the arithmetic process, and arithmetic process can be manipulated more conveniently as follows. You take an integer 41 and then divided by 2 and remainder is 1, and 20 divided by 2 is 10 and there is no remainder 0. You take 10 divided by 2 is 5, remainder is 0, 2 divided by 1, 5 divided by 2 remainder is 1, and 2 divided by 2 is 1, the remainder is 0, and 0 by 2 is 0, and then the resultant is 1. Therefore, the conversion of this one is what 1 0 1 0 0 1, this is what previously explained. So, another example, convert decimal 153 to octal, the required base r is 8. Now, start. So, 153 by 8 you have to do, the remainder is 1 and then 19 times it comes. So, 19 by 8 you have to take it, remainder is 3 and then the resultant is 2. Therefore, 2 is only number that you have to do that, hence there is a no value, therefore, put it 0. Therefore, it convert 2 3 1 base 8. So, that is the value of 153 base 8. Convert the decimal number to a binary. The process is continue until the fraction becomes 0 or until the number of digit has sufficient accuracy, right. For example, we have a number 0.6875 and then multiply with 2, so that the resultant will be 1.3750, separate integer and fraction, right. So, the coefficient you call it as a suffix minus 1, and then there is no integer, therefore, you take this number and then multiply with 2. So, we have a 0.7500 and corresponding integer value is 0, therefore, you take 0. Next is 7500 multiply with 2 and then it becomes 1.5000, integer is 1 and fraction is 0.5000, therefore, a suffix minus 3 is 1 and then 0.5000 000 multiply with 2, we have 1, therefore, integer is 1 and fraction is 0, therefore, a suffix minus 4 is 1. This implies 0.6875 base 10 can be written as 0.a minus 1, a minus 2, a minus 3, a minus 4 base 2, which is equal to 0.1011 base 2. Now, to convert decimal fraction to a number expressed in base r, and similar procedure is used. However, multiplication is a binary r instead of 2, and the coefficient found from the integer may range in values from 0 to minus 1 instead of 0 and 1. Now, another example 1.4 states that convert 0.510 base 10 to octal. So, 0.513 into 8 is 4.104. Now, we have a integer is 4 and decimal is 0.104. You take 0.104 into 8, so that 0.832 will come. Multiply 0.832 into 8, so that it becomes 6.656 will come. Here integer is 6 and decimal is 0.656, and multiply 0.656 into 8, so that the resultant is 5.248, and integral part is 5 and decimal 0.248, and multiply with the 8, so that 1.984, and then the integral part is 1 and decimal part is 0.984. So, 0.984 multiply with 8 is 7.872. So, this way we can express decimal part to the in terms of the octal, so that the resultant of 0.513 base 10 equal to 0.406517 and so on base 8. Now, from example 1.1 and 1.3, we have 41.6875 under base 10 equal to 101,001.1011 base 2. From example 1.2 and 1.4, we have 153.513 base 10 is equal to 231.406517 under base 8. So, this way we can convert into what base 8.